Hi, everybody, and welcome to today's online event. I'm Susanna Randall. I'm an astronomer here at the European Southern Observatory, ESO. And today we're going to be talking about ESO's extremely large telescope, the ELT, which is going to be the biggest optical infrared telescope in the world when it is finished. And we will have a bunch of experts that will be answering your questions. So please feel free to ask questions in the chat at any point, and we'll try and answer most of them. So the best telescope in the world will be nothing without the instruments that will record the signals that the telescope is catching. And that's why today we're introducing 2 out of 4 first-generation instruments for the ELT. We have first METIS, which is the mid-infrared ELT imager and spectrograph, and then also MICADO, the multi-AO imaging camera for deep observations. Together, these instruments will help us answer the biggest astronomical questions of our time. And who knows, maybe we'll even find evidence for extraterrestrial life. So we have a bunch of experts that will join me here during the next hour and that will be very happy to answer your questions. Let me introduce them. First of all, we have Michele Girasuolo, and he is the ELT program scientist here at ESO. Hi, Michele.
Hi, everyone.
Then we have, for the METIS instrument, Bernhard Brandl, who is the PI, so the principal investigator for METIS. That means he's responsible for the project as a whole, and he's also a professor of infrared astronomy at Leiden Observatory in the Netherlands. Hi, Bernhard. Then we have Jeff Lynn. He's the local project manager for METIS at NOVA, also in the Netherlands, in Dwingeloo. And he's responsible for the optics subsystem. And at NOVA, they're also managing the project, integrating the system, and testing, among other things. Hi, Jeff.
Hello, everyone.
Then the last person to join us for METIS is Silvia Scheithauer, and she's the local project manager for METIS at the Max Planck Institute for Astronomy, the MPIA in Heidelberg. And the group at MPIA is responsible for the METIS imager and also the adaptive optics system. Hi, Silvia.
Hello.
So that is the METIS team. Then I'd like to introduce the MICADO team. First, we have Rick Davies, and he's the PI, so again, the principal investigator for MICADO, and he's at the Max Planck Institute for Extraterrestrial Physics, just next door to me here in Garching. And the Max Planck Institute for Extraterrestrial Physics does the system engineering, builds the cold optics, and also leads some of the instrument's science themes. Hi, Rick.
Hello.
Next up, we have Nadine Neumeier, and she's a member of the MICADO science team. She's also a group leader at MPIA in Heidelberg, and the group is responsible for the relay optics and the MICADO data calibration, which guarantees that the data we get is of high scientific quality. Hi, Nadine.
Hi, everybody. Hi.
And last but not least, we have Eric Gendron, who's the adaptive optics scientist for MICADO at Paris Observatory. And his group is responsible for the design, manufacturing, and tests of the single conjugate adaptive optics module. Hi, Eric.
Hello, everyone.
So as you see, we're quite an international team. The experts here are distributed over 3 countries. And it will be really interesting to hear from some of the audience where you guys are from. So if you'd like to write in the comments where you are watching from, then, well, I think it will be very interesting for all of us to see where we have participation today. But first of all, we'll start with an introduction to the telescope itself. Of course, you can't have instruments without a telescope, or you could, but they wouldn't be very useful. So we'll start with an introduction to the ELT given by ESO's Michele Girasuolo.
Hi, everyone. Again, so I hope you can see my screen. Susanna, they can? I hope so. So a very, very short talk, but I would like to give you some brief highlights of what the challenges of building such a big telescope is, and give you a glimpse of the great science that the ELT will be able to do together with the instruments that you just saw. But let's start our journey from the north of Chile in the Atacama Desert, which is an extremely dry place. You know, it looks like to be on Mars. However, it's also one of the best places to study the stars and the universe. You can see in this picture the current best telescope that we have looking through the Milky Way, and that is one of the driest places on Earth where we can really look into the universe without being obstructed by clouds. And it's exactly in this north of Chile, in the Atacama Desert, where we are building our extremely large telescope. You can see here the top of what is called Cerro Armazones, a mountain of 3,000 meters high. And you can see there the construction of the telescope itself. And this project is an absolute marvel. It's a challenge in all the various aspects, from the science point of view, but also from the engineering point of view, how you design such a system, and also how the industry, industrial partners are able to manufacture some of these extremely complex components. And as you can see from this picture, we will also launch extremely powerful lasers into the upper part of the atmosphere and really create some artificial stars that we use with a technique called adaptive optics to remove all the turbulence, all the disturbances that the atmosphere itself generates. Somehow you can imagine, as with this technique, we are lifting the telescope above Earth, outside the atmosphere, to make sure that we can get extremely sharp images, like if the telescope was actually in space and not with the turbulence of the atmosphere in front of it. And this is a gigantic project, not just in terms of complexity and challenge, but also in terms of size. You can see here, compare the telescope to the Colosseum in Rome, and I'm sure many of you have seen the monument, and you can see it's more than twice as tall as the Colosseum, but at the same time is not static. The telescope itself needs to move to track the stars as they move across the sky, but at the same time maintaining an extremely high accuracy of the surfaces of the mirrors to be able to obtain very sharp images. That means that we have to move more than 3,500 tons of steel and glass, but maintaining an accuracy of all this wavefront to the order of nanometers. And that nanometer scale is something like 10,000 times smaller than a human hair. Can you imagine moving this enormous amount of structure but maintaining an extremely high precision? But why are we doing this? Why do we need such a big telescope? And the ELT has been built and thought with to answer some of the key questions in astrophysics, but would argue even some of the big philosophical questions for humanity. Are we alone in the universe? Are there some planets orbiting other stars far away from us that may have life on these planets? And ELT is so powerful that it's able, for example, to measure the chemical composition of the atmosphere, of this very thin layer of air on top of other planets, to see if there is possibility for life in this planet. But also will help us to understand how the stars form in the various pockets of the universe and how they evolve across time, maybe some of them exploding as supernovae or becoming black holes, and see how the stars will get together to form these beautiful patterns of galaxies that we see around us, this island in the universe, and not just our own galaxy or the galaxies around us, but up to the galaxies across the entire history of the universe, up to the very, very first galaxies ever formed more than 13 billion years ago and away from us. And also helping us to understand how these mysterious black holes grow symbiotically with the galaxy itself, how they grow, how they generate energy, and how they contribute to the ecosystem of the galaxy. These and much, much more is what the ELT will be able to do. And to do this, as I said at the beginning, we need the biggest eye on the sky. You can see here a picture of the telescope from the inner part of it. And what you see down there is the primary mirror, what we call the main mirror of the telescope, which has got a diameter of 40 meters, which is the largest ever built on Earth. And the mirror is so big that it's not possible to make it in a single piece, but we had to make it by individual segments. You can see there the segmentation pattern at the bottom. And each of this mirror is 1.5 meter in diameter, which is almost the size of a human person, and is made of a special material called Zerodur, because it does not need to change the shape as we change with temperature and as we look at the sky while we do this very, very detailed observation of the universe. And that is what the telescope does, but also, as we heard, the instruments are a vital part of the entire program, because the telescope collects the light, but the instruments are the ones that analyze these photons. They've been traveling for billions of years. And as you will see later, two of these key instruments are presented today. One is MICADO and the other one is METIS. And the entire project of the ELT can only happen in an environment like the European Southern Observatory, where there is a very strong partnership between various member states across Europe and even further away. And this means bringing together the best scientists, but also the best engineering and the best industrial partners to really build something spectacular. And the current status of the telescope itself is really progressing well. You can see here an image of what is the construction site on top of the Amazonas. You can see we are already more than 15 meters above ground, and this will progress very fast now with the construction of the dome itself. And that's what we have today, and in just a few years' time, that's what we will be able to have. The biggest eye in the sky for humanity to make a huge amount of discoveries. But I think more than anything else, what will be used as telescope is for discovering the unknown. What we still don't know, we still do not know what to look for, but maybe some of you young generation that are listening now will be the one that makes with us these great discoveries. And I hope all of you will be enthused by this fantastic new project. And I stop here.
Thank you very much, Michele, for this wonderful introduction. And I'm happy to report that we have people joining from as far away as Buenos Aires and India. So we have people from Amsterdam, as I said, Buenos Aires, Munich, of course, India, Turkey, Germany. So really people from around the globe, which is really, really nice. So we've heard a little bit about the ELT, and we're going to wait for more questions to come in and then answer them. I can see the questions popping up on my other screen. So we're going to wait a little bit, and we're going to first introduce the first instrument we're going to talk about, which is METIS, the mid-infrared ELT imager and spectrograph. And it's, which I find very nice, named after the Greek goddess of wisdom. And it's going to allow us to study a multitude of objects in the universe, as we're going to see in this mini documentary.
How did galaxies like the Milky Way come to be? How do stars and planets form? And are there planets nearby that could host life? These are some of the questions that ESO's Extremely Large Telescope, the ELT, seeks to answer. Set to start operating later this decade, the ELT will host a suite of high-tech instruments capable of matching its immense light-collecting abilities. Unique among them is METIS, the multi-tool instrument of the Extremely Large Telescope. METIS, or the Mid-Infrared ELT Imager and Spectrograph, will be operating in the mid-infrared. Infrared light can pierce through clouds of dust and gas to reveal what would otherwise be obscured. This allows us to witness the birth of stars and planets and peer into the center of galaxies to study their enigmatic black holes. METIS will specifically be looking at mid-infrared light. Hot objects fade away, and cooler objects like asteroids and exoplanets can be seen more clearly. This enables METIS to observe the atmospheres of those planets in more detail than ever before, in the hopes of finding habitable worlds. METIS is constructed with a 3-in-1 solution. First, it has its own adaptive optics sensor system, which works in tandem with the ELT's mirrors. It can measure turbulence in the Earth's atmosphere and correct for its blurring effects in real time. Then the light is guided either to a high-contrast camera that will create sharper infrared images than ever before, or it is directed to the METIS spectrograph, which separates the light into its constituent colors. It will provide very high resolution at unsurpassed sensitivity and allow scientists to learn the chemical composition and motion of astronomical objects. METIS is realized by a large international consortium in collaboration with ESO.
NOVA is the PI Institute leading the whole METIS instrument. NOVA is delivering a major piece of hardware, the Common 4 optics, which is essentially the first set of optics and filters in the cryogenic instrument. We deliver that to Leiden University, where our other 11 different partners are delivering their pieces, and we will assemble the whole METIS instrument.
There are numerous aspects why I really enjoy the work for METIS. One is working with the consortium. We have 10 partners from Europe, we have one from Taiwan, one from the US. Meeting all those different people, the different cultures, is a very inspiring experience. Then, of course, there is the technical aspects. We're really developing solutions to do something that no one has done before, using the biggest telescope on the Earth to do something. So that's certainly an inspiration.
The Max Planck Institute for Astronomy is responsible for the imager and the adaptive optics subsystem. So for me, the most exciting aspect is the scientific challenges which METIS will solve.
For such an instrument, you need, of course, mechanics, you need optics, you need control, electronics, you need a lot of programming, you need software. For a project of this size, which we have never done before, invest a lot of time in budgeting, in risk management, control of the quality to make the instrument a success.
METIS will weigh in at 18 tons, roughly the same as 3 well-padded elephants. Guiding the light through it requires a complex system with 243 optical surfaces, including over 55 precision-polished mirrors. In the end, the light will have traveled 36 meters within the instrument. All of METIS science modules are encased in a vacuum chamber that can cool them down. This is essential so that the infrared light emitted by the instrument itself does not contaminate the signal.
So cryogenic instrumentation is in general very difficult because we are cooling down optics and mechanics down to temperatures to 40 Kelvin, or this is minus 230 degrees Celsius. So this is very cold, it's not accessible. In addition, when you build mechanical parts that move around, they tend to not apply the same functions at cold. So you need to engineer them very carefully in order to have a robust instrument. And finally, it's also the whole thermal design. Cooling down things to that temperature requires a very thorough thermal engineering, and this is what we have to do with METIS.
METIS has many areas where it will do superior work, but there are 2 that are extremely important and unique for METIS, and that is protoplanetary disks and exoplanets.
METIS will be a frontrunner in exoplanet research, with a particular strength in taking direct images of them. It will be equipped with a set of highly specialized coronagraphs that can shield the bright light of a star to reveal its fainter and cooler planets. With this technique, METIS could ignore the beacon of a lighthouse and identify a firefly next to it.
2 main things where the ELT will be completely game-changing. So one of them will be the characterization of the planets that are already known. So we will be able to provide much deeper insight into the atmosphere of these planets, which will tell us how they formed and how they evolved, what they are made of, possibly even find some possible signs of things that might relate to life. The second goal of METIS will be to find smaller planets down to rocky planets, terrestrial planets, where life could possibly form.
So the main science goal for exoplanets with METIS will be to contribute addressing the key question of the formation of planetary systems. We will also be able to observe planets that are further away from their parent stars and obtain spectra for this planet that we cannot have today.
Because of the light collecting capabilities of the ELT, the METIS spectrograph will be able to detect elements and molecules in the atmospheres of exoplanets. It can do this within just a few hours of exposure and therefore observe planets at a much higher pace. But crucially, since METIS operates in mid-infrared, it is dedicated to observing cooler exoplanets with temperatures approaching Earth's. This will make it a game changer in the search for habitable worlds. The ELT and JWST will complement each other in the mid-infrared wavelength. JWST is able to detect fainter objects and covers a much larger field of view, whereas the ELT will provide sharper images and a higher spectral resolution.
We will be able, with a METIS instrument, to probe planets that are not accessible by the James Webb Space Telescope. So having both those two instruments allow us to better understand this exoplanetary system.
The quality of the collaboration in the METIS consortium is higher than most projects I've been on in the past. And I think this leads to our success. It'll be extremely fulfilling to see all the different pieces come together. The biggest thing is feeling the joy for the team.
It's a long way. It's something like 15 years from the start of the project till we finally will have it on the mountain. And this is a moment I really look forward to.
I certainly dream of standing on this platform and seeing the telescope and the instruments working together. I think that must be extraordinary just because of the size.
I'd be very excited if the next generation of astronomers use the instrument and write great science papers of things that could not have been possible otherwise. If they are excited about the instrument, use it and find something that no other instrument, no other telescope could have found.
The ELT's multi-tool instrument METIS will become an invaluable asset to help us understand the cosmos. It will let us peer into the birth chambers of planets and stars. It will study the evolution of galaxies, the atmospheres of exoplanets, and make us rethink our place in the universe.
Talking about a place in the universe, I have a quick update on the countries of people that are joining us. So we have people joining us from Australia, the US, Denmark, France, and Italy, as well as the countries I previously mentioned. So that's fantastic. And now we're going to start our Q&A session on METIS. So first of all, my first question is for Bernhard, and I would like to ask, of course, the obvious question, what is the most exciting discovery you expect to make with your instrument? And in particular, North Star Space Art wonders, are you going to take a direct image of Proxima Centauri b?
Yeah, excellent question. Now, of course, first of all, the most exciting discovery is the one we don't know yet what it will be. Right? If we would know, then I think part of our excitement and work would already be gone, or would be boring. We're doing this because we're really exploring new territories in discovery space with the biggest telescopes, expanding the wavelength ranges, better instruments, more sensitive detectors. There must be something we don't know yet, right? And it's these breakthrough discoveries that are most exciting. Now, apart from that, I would think the Proxima b question is much related. We definitely want to use METIS to look at the nearest star system of Alpha and Proxima Centauri and look for planets. Well, we already know about Proxima b, but maybe there are more. Maybe there are more convenient planets to live than Proxima b, and this is certainly something we can explore with METIS.
Yeah, well, probably Proxima b is not the nicest place to live on, right? Because of the flares of the star. But who knows? Maybe Alpha Centauri also has planets the Earth size. We don't yet know. We might be able to find out with METIS.
Absolutely. Yeah, and they would be most easily detected. Well, easily with in quotes, with an instrument looking at thermal infrared wavelengths, because presumably if those planets are habitable and have similar conditions than the Earth, they would also be around the same temperature in the Earth, and the Earth emits most own thermal emission most prominently at those wavelengths that METIS is sensitive to.
So METIS might discover Pandora, the real Pandora from Avatar.
Yes, so if our nearest habitable neighbor is called METIS 1, I would be happy.
It's fantastic. Okay, let's come to a bit more of a system engineering question. This one's for Jeff. So we heard about how precise the instrument has to be. So how do you coordinate such a 2 millimeter precision construction? And this question is asked by someone whose name I can barely pronounce, Eseritos 12.
Yes, that's a great question. We've had experience in the past on smaller instruments, and with modern computer design, you can get very accurate. It's very important also when you have large consortiums. So you have many different partners bringing their pieces together, and you need to make sure everything fits just carefully. So a lot of analysis is done on computers to make sure it all fits. The challenge with the ELT instruments, though, is that instruments are 2 to 5 or 10 times larger. Yet at the same time, we're still trying to have this millimeter, or a lot of times even sub-millimeter precision. And that's where the real design challenge comes in. And that's the fun part for us engineers and the managers as well, is to make sure this all comes together. But there's lots of coordination needed, both in computer design and documents written to make sure it all comes together.
And a follow-up question from me, just because I'm curious. This giant will be constructed in Leiden. How are you going to get it all the way to Chile and to the ELT, which is on top of a 3,000 meter high mountain?
Yes, indeed. So there's different shipping methods. Of course, getting it all the way to Chile, we could fly it or we could ship it. Our current plan is to put it on a ship and send it over that way, similar to how James Webb was sailed over there from the US. So, and we plan to keep all the instrument in the cryostat, put it in a cage, a shipping structure and frame in a special shipping container, and ship it over there. And then the structure that holds the vacuum chamber up, that'll all have to be constructed on the ELT. But we tested in Leiden. We test the construction, the fitting, the fit checks, and everything, so that we hope everything goes perfectly smooth at the ELT.
Yeah, I guess it'll be a very exciting time when the transportation's ongoing. So even more technical question for Sylvia, and this is asked again by someone whose name I can't pronounce, Hudenbusk or something. How do you supply the coolants to the mid-infrared instruments?
Yeah, you could see very well on the video that METIS has a big cryostat, so the size is approximately 3 meters in diameter and height. And inside this cryostat, there are the scientific instruments and the wavefront sensor and all the 4 optics. So the heart of the instrument is inside the cryostat, and it is cooled down to minus 200 degrees Celsius. And so we have big cryo coolers, and we use liquid nitrogen for this. So the ELT has to provide very much of liquid nitrogen, and it will take several days to cool it down. And so the overall temperature in the cryostat will be, as said, minus 200 degrees Celsius, but the imager instrument needs partially even to be cooled more. So it will be minus 230 degrees Celsius, as our NVENT detector needs this low temperature to operate. So, but yeah, it's liquid nitrogen and cryocoolers.
Yeah, it's very impressive thinking about how cold these instruments have to be, because of course in the infrared, everything is glowing basically on Earth, right? So if you don't cool the instruments really down to just above 0 temperature, you'll just get loads and loads of artifacts and not actually be able to observe the universe. So we also have some more general questions on the ELT. So I'll take the opportunity now to ask Michele. So one of the questions is, well, I think it's a compliment, first of all. It says, such a beauty by Axmime. I presume that refers to the ELT, so it's a beauty. How much does it cost, and how many jobs will it create? And do you have any information? Apparently, this person wants to come and work for us. Do you have any information about careers?
The overall project cost about 1.5 billion euros. And what's happened is really creating a lot of works all over Europe. So there is the work of the engineers that are designing the things. There's the scientists, they are trying to think how to use it and how to help the engineers to make the best out of this. There's a lot of work generated by this into the industry. So we have to produce these big structures, metal structures. There's a company doing that. There's another company producing the glass, another company polishing it, another company getting the electronics. So there are thousands of people involved in the ELT all over Europe, directly or indirectly connected to the project. And if you are interested in either science or engineering and working either ESO, but also in the consortia, because these institutes are the ones that are really helping us to build these Telescope Plus instruments. Of course, there are always some calls on the ESO website. There is a tag called career, and I'm sure all the other institutes also always looking for help to building these big giants. So you're more than welcome to come and work with us.
Yes, I guess there'll be very many interesting jobs coming up over the next years and even decades with the ELT. So we have another question, which I find very interesting also as an astronomer, by Greg Oo, which is a very unusual username. And this is about, I assume, METIS. So this is a question for Bernhard again. And the question is, will METIS perform blind surveys too? So you talked about discovering the unknown, what we don't know. So are there going to be blind surveys?
I think the short answer is not really. And it just illustrates why we have several instruments on the ELT. None of these instruments is cheap. Nevertheless, ESO wants several there because they're all complementary to each other. Some are designed to do the best in blind surveys. Some do the best in looking deep into the universe. Some are the best in finding nearby interesting objects. Now, METIS is more of the latter category because the sensitivity that we achieve in the thermal infrared from the ground is not competitive with what the James Webb Space Telescope will give us. But we have a much higher angular resolution, so we see a lot sharper, and we have a much higher resolution spectrograph. So we're really superior in some areas, but not in all. And because of the high thermal background that we're having to face, I think these blind surveys are better done either at shorter wavelengths, for instance, with Mosaic, as we will hear soon, or with the James Webb Space Telescope. So all these instruments have their own areas where they're unsurpassed, I think. And so blind surveys is not for METIS, sorry.
But still, it's an answer, so thank you very much. You talked about the resolution. So what will the resolution be in arc seconds on METIS?
So I think it's about 20 milliarc seconds. So that's about a 50th of an arc second. And an arc second is if you take one of your hair and just hold it at 10 meters distance. That's then more or less the diameter of the hair. An arc second So you slice your hair 50 times and then you look at it. That's what we get.
That's quite unbelievably impressive, actually. And
well, there is a reason to spend those 1.5 billion that Michael was referring to.
Yes, and the whole thing is only possible because of the adaptive optics system, right? I mean, that is one critical thing that both the instruments have that maybe we'll talk about a little bit later with MICADO again, because otherwise we would have to be in space to get that kind of fantastic resolution. So one last question for Michele, because I think we have to move on to MICADO, but this is the question I think everybody wants to know, and I don't know whether you can answer it even, but that is by Laurent Pinard. And the question is, which instrument will be the very first working on ELT? And then together with that, a question by Gaurav Gayakwat. Sorry, I probably completely mispronounced this. When will this instrument and the ELT be fully operational?
So at the moment, you see, we are constructing and we are forecasting that the first light will be in 2028. And currently, MICADO is the instrument that will be the first light imager for the ELT. So we hope in just 5 years from now to point the ELT with MICADO attached to it and get some beautiful images of the universe.
Fantastic. Well, that's quite apt because the next instrument we're going to be talking about is MICADO. And I have to say, I love the name, and I think it needs no introduction because at least I, as a kid, loved the game of MICADO. So I think it's a fantastic name for the instrument. And MICADO will be able to image very distant galaxies and also look at the center of our galaxy and the area around the black hole lurking there. And in the following video, we're going to see more about this.
How many black holes are there in our galaxy? How did the first stars form? How did the universe come to be? These are some of the questions that ESO's Extremely Large Telescope, the ELT, seeks to answer. Set to start operating later this decade, the ELT will host a whole suite of high-tech instruments capable of matching its immense light-collecting abilities. Unique among them is MICADO, the super camera of the Extremely Large Telescope. MICADO stands for Multi-AO Imaging Camera for Deep Observations. It will study exoplanets, distant galaxies and stars, and investigate black holes such as Sagittarius A star at the center of the Milky Way.
The ELT, the largest telescope in the world, will have fantastic capabilities in terms of collecting the light. But the best telescope in the world can only be as good as the instrument at its back end, which actually then detects the light and analyzes it. And MICADO is a camera simply built to make optimal use of the ELT.
MICADO is a 20-ton science machine, 6 meters high and roughly the size of a small house. It is designed and built by an international consortium with over 150 people from 6 different countries under the leadership of the Max Planck Institute for Extraterrestrial Physics in Germany.
Within the consortium, we are so many partners and everybody has over one portion of the instrument. And we will have to design everything that is complementary and working properly together. When we put it together, everything has to fit and work.
150 people in 6 countries working on this project. We're working for a telescope that's not yet there yet, and everyone in the project is used to building instruments for a telescope that already exists, and this is a very different way to work.
So in astronomy, it's always about building a prototype. Companies normally have the nice thing, they build a prototype and then they optimize it until they can sell it. We have to build a prototype and it has to work. And this is, I think, a very, very big challenge. That's why a lot of people with a lot of experience work on things like this.
MICADO uses an ultra-sensitive infrared camera with high-resolution imaging capabilities to investigate cosmic objects that are obscured by clouds of dust and gas. Unlike visible light, radiation in the infrared can pierce through the clouds and reveal what would otherwise be shrouded in darkness. The infrared light is captured and fine-tuned by the ELT's mirrors and then fed into MICADO through a secondary instrument that corrects the blurring effects of the Earth's atmosphere in real time. The whole process enables MICADO to obtain extremely sharp images.
MICADO will have these three components, the imaging, the spectrometer, and will also enable to make precise astrometry. For the imaging, the resolution will be about 10 times larger than what we have with current 10-meter telescopes. And so that means not only the ELT will be the biggest eye on the universe, but MICADO will make sure that it's going to be the sharpest eye on the universe.
If you think about the resolution of this instrument, if I told you it was 10 milliarc seconds, that doesn't mean anything. If I said we're here in Munich, if you could imagine looking at someone in Berlin 500 kilometers away and they held up their hand, you'd be able to resolve the width of their finger. This is how fine the resolution is.
After correction, the light passes into MICADO's ultra-cold heart, the chamber where its infrared detectors are housed. This cold chamber is around 2 meters in diameter and keeps the detectors at a frosty -200 degrees centigrade.
We're observing in the infrared, so we're detecting heat. And because we're detecting heat, we need to have all our optics and our detectors cooled right down so they detect the heat from the astronomical objects and not the heat from the instrument itself.
Only by keeping cool can MICADO sense even the faintest infrared signals. Its immense increase in sensitivity will enable astronomers to discover stars previously too dim to be detected, and to peer more closely at exoplanets previously hidden by their brighter stars.
MICADO will directly image exoplanets around a variety of stars nearby, and not only the more giant planets, but really go to twins of Earth planets.
Not only can MICADO see in the dark, it can also see with stunning clarity. The size of the ELT's primary mirror, 39 meters in diameter, allows it to obtain extremely high-resolution images. Thus, MICADO can tell individual stars in crowded clusters apart and reveal details in distant galaxies. At the center of our galaxy, MICADO will detect stars increasingly closer to Sagittarius A star.
This is one of the really exciting things because the resolution of this instrument is so high, we can measure proper motions of stars very, very precisely, much better than any other telescope.
MICADO will be able to perform with the same sensitivity as the James Webb Space Telescope, but with 6 times the resolution. This will allow astronomers to capture ancient light from the very first stars, just as they began to shine, giving us hints about the origin of the universe.
James Webb will discover many very remote galaxies, for example, or very faint stars and galaxies nearby, but it will not be able to look at them in detail. And so with MICADO, we will go after those objects. And so the James Webb will tell us the when and the where, but we, with MICADO, will be able to tell the how.
We're thinking about things we know now. What's most exciting is the things we haven't thought of yet, the discoveries we'll make that we haven't anticipated.
It will open up a new space for discoveries that we may not even think of now. That happened to me in the past, luckily, and I hope that will be the case again.
The ELT super camera MICADO will become an invaluable tool to help us understand the cosmos. It will take us closer than ever before to the supermassive black hole at the heart of the Milky Way. It will give us a look at the first remote galaxies that formed after the Big Bang and make us rethink our place in the universe.
So we heard that MICADO is going to be a super camera. So I have an immediate question for that, of course, and that would be for Rick. What makes MICADO a super camera? And that is very similar to the question by I Heart Kiwi, which says, is ELT, let's say ELT plus MICADO, better than JWST? We heard the resolution would be better. Is it the best one yet?
It will certainly be the best one. MICADO has two things that make it better than any other camera we have, and that's its sensitivity and resolution. The resolution comes from the size of the telescope and using adaptive optics to correct the blurring in the atmosphere. And the sensitivity comes from polishing mirrors. We push the limits of technology to get these mirrors as highly polished as possible, and then we cool the instrument down to liquid nitrogen temperatures to reduce the background. And so you get very high sensitivity and very, very good resolution. If we compare it to JWST, and over the last year, everyone's got very excited by the images that JWST has produced, we're going to have the same sensitivity, but we're going to have 6 times better resolution. What this means is when MICADO goes on sky, you're going to look at the images that are 6 times sharper and compare them to what JWST has produced and say, oh, JWST images, they're all blurry.
Which seems unimaginable right now. But that's the great thing about building newer and better telescopes and instruments, that the things that you thought were not possible suddenly come into focus and become possible. So we heard that all of this, and I mentioned this briefly earlier, is only possible due to the very complex adaptive optics system. And I have a question for Eric related to that. And this is from Timmy, a very easy name to pronounce for once. And it says, what functions do the laser beams have? Eric, I think you're still muted.
Oh, you're right. Yeah, I understand these questions because the lasers are quite mysterious. So the role of the lasers is to create in the sky an artificial star. This star is required to get the adaptive optics system to work at its best. So as incredible as it may sound, that there are not enough stars in the sky for adaptive optics. The reason is that adaptive optics needs a sufficiently bright star to be able to work properly, while the ELT will observe the darkest regions of the sky, where there are only very faint stars. So those lasers have their wavelength, their color, tuned exactly on the color of the sodium atoms. And it turns out that the atmosphere of the Earth contains a layer at 90 kilometers altitude with sodium atoms. When the laser beam crosses this layer, it makes it shining just as if it was a new star that the adaptive optics system is using. So that's the reason why we have those all those lasers.
Thank you. And actually, I have a very closely related question from Roberto Volsa, who says, and this is possibly also for METIS, but I'll ask it for MICADO. So it says, MICADO and METIS are provided with their own adaptive optics systems, which means ELT is different from other telescopes such as VLT, where adaptive optics is provided from the telescope and not from instruments.
Yeah, it's a technical choice. Actually, it's not exactly true because one of the main components of the adaptive optics system, which is the deformable mirror, is located inside the ELT. So the core of the adaptive optic system is really inside the telescope and is available for all the instruments behind. And each of the instruments provide their own wavefront sensor, which is the second important component that makes the adaptive optic system to work. So in the ELT, the adaptive optic system is really distributed across all the telescope, one part inside the telescope, the other parts in each of the instruments.
Thank you very much. So it's basically the combination of ELT and the instruments that makes the full adaptive optics system work as it does.
Exactly, yeah.
So slightly related to this, coming back to the ELT, a question for Michele, a very general question, and this is from Markus Nielbock. His question is, what is the ELT's slewing speed?
It's a massive structure, and you might think that it will take ages to move, right? But actually it goes quite fast. In just a couple of minutes, it can do a 360, and you would be amazed by how smooth all the motion is. There's now some prototypes been built, and you see this massive structure move effortlessly, really smooth, no a single noise, nothing. And that is the key to maintain all these vibrations and not disturbing the observation itself. So it's a marvel of engineering.
Yeah, there's nothing quite like, I mean, I have it even at the VLT. You see this huge thing moving and it's just soundless. I mean, it's incredible. So I can't wait to also see that for the ELT. It's going to be incredible. But coming more to science now. So one more question from Michele on the ELT. Will the ELT be able to look at moons in our solar system, such as Titan and Europa, to search for life on these moons? And this is a question by Alexander Heinz.
Yes, the ELT is designed also to look at objects in our own solar systems, and there's an entire branch of science that looks at the solar system science. Looking for life, I'm not sure directly looking for life, but I think what will happen is going to be very complementary to the ESA mission. So there's a mission going to these moons that are trying to observe something, and what we do, we complement our observations with much higher resolving power in spectroscopy, but also detailed imaging for these things, and providing the long-term temporal observations. While a mission goes there for a year and then that's it, what we do, we provide the long-term observations for all the moons of our solar systems. That's a big science case for us.
So yeah, so we're going to be complementing the space missions that are actually going to these places. Although yes. I think the most exciting part would be if at some point in the future we manage to drill into the ice and actually look below the very thick ice crust that these moons have. I mean, but I think that's far in the future.
We look at the plumes coming out from here.
Yes. Okay, so a more general question, and I think Nadine has agreed to take this from Dr. E. Kiran Kumar. And it's a question I like a lot because it's slightly philosophical. Will it, I assume the ELT and MICADO in this case, make our world a much better place to live in? Is it only to feel amazed at this universe, or does it actually have any practical use for our world?
Yeah, well, to take this question, I think it's actually a great question. But I think actually science is there to make the world a better place in general, right? So we've seen a lot of scientific progress in the past. And astronomy in general, this is actually, it's the science that we are thinking of our place in the universe. Like, where is it coming from? How does it develop? Actually, it's a cultural building science, right? So we want to see where this goes, like how does the universe develop, and yeah, how did it begin? So with MICADO, we will be able to actually look very far into the past of our universe. So I think this is one of the aspects why I think actually this telescope will be like a game changer in so many respects, because we can see, also, for example, the science case of finding life on other planets is a super fascinating thing for our, human beings. Maybe we see, other extraterrestrial life. But I think in like a bit more practical sense, I think such a big endeavor of such a huge instrumentation project, it brings, so many different countries and cultures together. So seeing humans work together, for a common purpose, I think that in itself is actually making the world a better place.
And I think that's a wonderful phrase to close on. We'll make the world a better place with the ELT. So I'd like to thank all of you, all the experts, both for METIS and MICADO, and of course Michele, very, very much for taking the time to be here, answer these questions, and of course the amazing work that you guys are doing on the instruments and on the ELT. I'd also really like to thank our audience, which has been really furnishing us with very creative and very interesting questions. So it was a lot of fun hosting this event. So I hope you also had fun. And don't forget to follow ELT updates on the YouTube channel and also on the webpage to make sure that you stay up to date. Me and the experts will try and answer some of the questions that we couldn't answer here. In the interest of time, we only selected a few questions, but watch the spaces. We will be posting answers to some of the questions. And at this stage, I say goodbye. I hope you have a nice evening in Europe, morning, night, whatever. See you next time.